Hello everyone, welcome to this video. In the previous videos, we have seen certain properties for Laplace and inverse Laplace transform. We had seen that if the given function was f of t, then its Laplace transform is defined by capital F of s. Moreover, we saw the first shifting property which says that Laplace transform of e to the power at into f of t is equal to capital F of s minus a. Then the Laplace transform of t to the power n f of t, that means some function multiplied by some power of t, that is equivalent to minus 1 to the power n, the nth derivative of the Laplace transform of this function f of t. And then we had discussed, if you divide some function f of t by t to the some power n, right, this is some arbitrary power, in that case its Laplace transform would be equal to taking the integral of the Laplace transform of f of t n times, right? For derivatives, we have seen that the Laplace transform for the first derivative is defined using this expression, for second derivative using this expression, and the nth derivative is given using this relationship, right? Where these are f of 0, f dash 0, f to the power n minus 1, 0. They are the derivatives of the function f calculated at the point 0. Okay, and the last property, we know that the Laplace transform of integral of f of t, that come out to be f of s divided by s. So that means whenever you multiply by t, you have derivative. Whenever you have derivative, you have multiplication with s. And whenever you divide by t, you have integral, and whenever you have integral, you divide by s. So this is the general relationship that you already know between the Laplace transforms. And similarly, we have these relations inverted for this inverse Laplace transform. So as of now, how this Laplace transform is useful in order to solve the ordinary differential equations. Or in other words, I can say that how can I use this ordinary differential equations how can I find the solution of these ordinary differential equations using Laplace transform. So this is the main topic for this video. So I have listed some general steps in order to solve differential equations. The first step is to take the Laplace transform of the given ordinary differential equation, and then once we apply the Laplace transform on the equation, what we do, we simplify that expression in the s domain, and after simplification we again apply the inverse Laplace transform onto that. So basically what we are doing, we are moving from t domain to the corresponding s domain using this Laplace transform, and then we are performing simplifications here. After performing the simplifications, what we are doing, we are again applying this Laplace inverse onto the function that we obtained after simplification. So that will result in the solution here in the t domain of the given differential equation. Okay, so this is the general terminology. Let us move on to calculating the solution for this ordinary initial value problem using Laplace transform. So for that, I am considering this equation y double dash minus 4y dash plus 4y, that is equal to 64 sine 2t, where you are given y at the point 0 is equal to 0, and you are also given its derivative, first derivative evaluated at the point 0. So this is the information that we have, and this equation is to be solved using Laplace transforms. So for that, this is our equation. The first step is the application of Laplace transform on both sides of this equation. So when you apply Laplace transform on both sides of this equation, you will have Laplace transform of this whole equation. Now because this is a linear operator, so in that case you can write this to be the Laplace transform of individual terms, where you have taken out the constants. Why? Because this is linear operator, so you can separate out all the terms, right? So now we have to perform the Laplace transform. So what is the Laplace transform for y double dash? Before applying the Laplace transform here, let us suppose that the Laplace transform of the function y of t, that is given by capital Y of s in the s domain. So according to that, we know the formulas. The Laplace transform for y double dash is going to be s square y of s minus s into y of 0 minus y dash 0, and the Laplace transform of the first derivative of y is s y of s minus y of 0. Okay, so we have just substituted the value, this one in place of this second derivative, this, and in place of this first derivative we will substitute this value, and we know what is the Laplace transform of y. That is it is capital Y of s. So accordingly we have this quantity, and moreover the Laplace transform of 64 sine 2t. Now 64 is constant, could be taken out. So we are left with sine 2t, and you know the Laplace transform of sine at, that is nothing but a divided by s square plus a square. So we have this quantity. Now the thing that is remaining here is to substitute what is the value of y of 0, y dash 0 and y of 0 here. So here if you look at the given conditions, y of 0 is given to be 0, so you can substitute the value directly, and y dash 0 is given to be 1. So you could also substitute this value over here. So once you substitute the values of 0 and 1 and 0 here, so we can simplify the expression in terms of y of s. So we can take all the terms containing y of s on one side. So that means you will, when you simplify this, you will have the coefficient of y of s as this term, and moreover all the other terms you can shift to right hand side so that it becomes equal to this particular term. So we have simplified the given expression in terms of y of s, and it comes out to be this particular quantity. So now you have the expression for y of s. The next simple step is to apply the inverse, this inverse Laplace transform. Now in order to apply inverse Laplace transform on this equation, you just have to firstly you have to solve this right hand side using partial fractions. Now how do you apply partial fractions is the major question here. Now here you see in the denominator you have this square term and this quadratic term. So according to the square term, you can calculate these coefficients, right? So you will write this to be as plus b divided by s square plus 4. This is according to this particular term, and for this term what you will do, you will write the terms like c divided by s minus 2, and then you have d divided by s minus 2 whole square. So you could substitute this term equal to all these quantities, the sum of all these quantities, and you can then evaluate the coefficients here a, b, c and d. So the final result comes out to be this quantity. Okay, so you have y of s like this. Now we will move on to our third step, which is the application of inverse Laplace transform on both sides. So we'll apply this inverse Laplace transform operator on both sides of our given expression, this one. So you will have Laplace inverse of capital Y of s and Laplace inverse of this whole quantity over here. So you have this thing. Now we have defined the Laplace transform of y of t as capital Y of s. So that means its inverse Laplace transform would be equal to y of t, which was desired. And because inverse Laplace transform is also a linear operator, so you can also separate out the terms and take out constants out. So that means you have to perform Laplace inverse of 1 upon s minus 2. Now you know the Laplace inverse of 1 upon s minus alpha, that is e to the power alpha t. So accordingly here we have, instead of alpha, the value 2. Therefore its value is e to the power 2t. And here we will apply the first shifting property. So according to first shifting property, what is the Laplace inverse of 1 upon s minus 2 whole square? It comes out to be e to the power 2t, this term, multiplied by the Laplace inverse of 1 by s square, right? And what is the Laplace transform of 1 by s square? That is simply equal to t, right? And for in the last term, it would come as such, and instead of Laplace inverse of s by s square plus 4, this is the Laplace transform of cos 2t. Why? Because you know this formula, Laplace inverse of s divided by s square plus alpha square, that is equal to cos alpha t. So accordingly we have cos 2t here. So this is the final solution of the differential equation, initial value differential, ordinary differential equation that we were seeking. And you saw solving this differential equation becomes much more easier using this Laplace transform, and that is what we intended to do over here. Now let us have a look at one more question where instead of this initial values, we are now given the boundary value. Suppose these are given to be the boundary value. So you are given some kind of interval in which you are to find the solution. So the value of the unknown is defined on the left boundary and on the right boundary. So let us have a look here. In this question, we are to solve this differential equation, d2x by dt2 plus 9x plus cos is equal to cos 2t, and we are given x at the point 0 is equal to 1. So that means here first of all you should know what is dependent variable, that is x, and the independent variable is t. So that means according to this condition, whenever t is equal to 0, the value of x is equal to 1. So here we are given this interval, the value of t is defined to be in the interval 0 to pi by 2. So at this left boundary, the value of dependent variable is equal to 1, and at this right boundary, the value of dependent variable, that is x, that is equal to -1. This is given to you, and here x dash 0 is not available. So what we will do, you'll see that in a moment. So before going on to that, let us first apply the first step, which is this given equation. We'll apply the Laplace transform onto it on both sides of this equation. So when you apply the Laplace transform operator on both sides, you will end up by Laplace transform of d2x by dt2 plus 9 times the Laplace transform of x, that is equal to the Laplace transform of cos 2t. Why? Because we know Laplace transform is a linear operator. Okay, so we have this thing. So now we can solve out this Laplace transform. If you assume that the Laplace transform of small x of t is equal to capital X of s, in that case you can write this to be s square x of s minus s x of 0 minus x dash 0, right, using this expression. And you could write there is no first order derivative, so this formula is actually not required here. So we will directly write plus 9x of s, that is equal to the Laplace transform. Its Laplace transform is s divided by s square plus 4, right? So now here we will substitute the values of constant. What are those? That means we will substitute x is equal to 0. X is equal to 0 in the question is given to be 1, but we are given another value at pi by 2 is equal to -1. So that means this particular term x dash 0 is not available to us. So what do we do in this particular case? This is not available. So in this case, we'll assume x dash 0 to be equal to 1, so that this quantity becomes minus a over here. And at the end, we will find out what is this particular value for a using the given condition, given boundary condition, right hand boundary condition. Okay, so we'll move by solving for x of s in a. So that means a will go as such. Then we'll simplify in terms of x of s. So we'll collect all the coefficients for this x of s. That turns out to be this particular quantity. So the next task is to form the partial fractions and separate out the terms. Why? Because applying Laplace inverse on the separated term would be more easier to give you the results, right? So we'll compute this using partial fractions. So I hope you can perform this partial fractions. After applying partial fractions, you end up with this particular term. So the next task is, after simplification in x of s, we are now ready to evaluate the value of x of t, which would come by taking the Laplace inverse of capital X of s. So we will apply inverse Laplace transform on both sides for this expression. So when you apply inverse Laplace transform on both sides, so that means you have, instead of this, small x of t, which is the required solution, and then when you apply inverse Laplace transform on this term, and this term, so you will have the Laplace inverse of s by s square plus 4, that is equal to cos 2t, the Laplace transform of s by s square plus 9, that is equal to cos 3t, and the Laplace transform of 1 divided by s square plus 9, that is equal to sin 3t by 3, and we'll treat this a to be some constant which is to be determined at the end. So finally you obtain this solution, but this a here is unknown quantity and we are to determine it through the given condition. So now what is the condition that is given to you? We are given x at the point pi by 2 is equal to -1. So this is the condition. So we'll utilize this condition. So wherever we have t, we will substitute in place of t the value pi by 2, such that this quantity x of pi by 2 is equal to -1. So accordingly, we evaluate the value of a from here, that comes out to be equal to 12 upon 5. So accordingly, you will substitute this quantities in the given equation star, so that you obtain, after simplification, the value of a to be 12 by 5. So you will substitute this value back here. So this becomes your final answer, right? So this is all for this video. I hope you understood this concept of solving both the initial and the boundary value problems, ordinary differential equations, using Laplace transforms. Well, that is it for this video. Thank you for watching.